Okay, on today's lesson, we want to talk about a very important concept in electrostatics, which is polarization. In this case, we are going to be talking about materials that are called dielectrics. And what we want to introduce first is the idea that maybe matter could be made of dipoles, okay? This will be the hypothesis that we will be using in this video. Okay, we will be thinking that the material, the dielectric material that we are working with, it will be made of dipoles. Okay, but what does that mean? Well, that means that, for example, look at this figure that I have here. This could be a material of a random material. Okay, but these things that I have here, are the molecules that compose that material. So those molecules, if you see, I represent the positive charge with a plus and the negative charge with a minus. So these molecules are represented as dipoles that compose the material, okay? So this dielectric is made of dipoles. So we want to study the case where, for example, we approach an electric field, okay, to that material. What will happen with the dipoles that made the material? Well, for example, if we approach a set of positive charges, well, these dipoles will be oriented in this specific direction, okay? Positive charges will be far from the electric field, okay? And the negative charges will be pointing to that electric field. So these dipoles get oriented by the electric field generated by this set of positive electric charges. Okay. In the case we will have some individual electric charges. Well, what we will get is that electric positive charges will be on this side of the material, and on the other hand, the negative charges will be closer to the electric field generated by the positive charges here. Okay, so in this case, this phenomenon is called polarization. Okay, we say that the material is polarized. Okay, so if our hypothesis is correct, then the dielectric will be polarized in the presence of an electric field. Okay, but looking that the material is made of dipoles, and this material will also have a volume, we can say that there is a density of dipoles, okay, like a quantity of dipoles per unit of volume, okay? So that is what we are going to call polarization. So the polarization will be defined as the derivative of the dipole moment with respect to the volume, okay? So in general, this expression is shown in this way, okay? So we need to know that in this case, the total dipole moment of the dielectric can be calculated with this integral over here. It's a volume integral of the polarization. Okay, so this will be like the total dipole moment of the dielectric. Perfect. Okay, but looking at, we have kind of like a total dipole of the material. We can remember that we have already encountered an expression to calculate what is the electric potential generated by a dipole. Okay, we have made that on a previous video. You can see that in the video of electric multipoles, for example, and we showed that, the electric potential due to the dipole is going to be the next equation. Okay, is this equation that we have here. But we have now defined the dipole as, the polarization times a volume differential. So this can be equal to, the polarization dot R divided by 4 pi epsilon 0 r squared dV. Okay, but what does this exactly mean? Let's say that, for example, we have a volume, well, a material that has a volume and a surface S, it has a volume V, and we have the reference system, for example, here. Okay, then, well, we are going to have a distribution of charges in this material. So we want to locate that distribution with a vector r prime, and then we want to calculate the potential on a certain point of the space P, for example, located by a vector r. And remember that the vector r is the one that goes from the distribution to the point where we want to measure the electric potential. So this will be r. And here we can locate a differential of volume, okay, which is the one that we have here in this expression. So we see here that to calculate the electric potential, well, we need to take the integral on that volume of the polarization dot r divided by 4 pi epsilon 0 r squared dV. Okay, and well, we are going to use a very famous formula that for now we are not going to show, but I'm going to write it here. Is the one that says that the gradient of 1 over r, okay, r of course is the magnitude of this vector here. Well, the gradient of this 1 over r, it will be equal to negative unit r all over r squared. Okay, we are going to use that formula that for now, again, we are not going to show. But you need to know that, well, in electromagnetism, we often use some relative coordinates to express some functions that are useful in many problems. In this case, we want to, first of all, introduce a function f of x, y, z, which is a function of the space. And we want to see what happens when, for example, we make a displacement of the reference system by a change of coordinates like x minus x prime, y minus y prime, z minus z prime. You're about to see why. But in this case, look that here we have the gradient of a function. Okay, so we are interested in calculating the gradient of this function f. You're about to see why. But what happens if we want to take the gradient now of this function that we have here? First of all, let's say that this function can be called as a function of x, y, and z, uppercase. Okay, so for example, well, we know that the gradient of f will be the partial of, with respect to x, of f in the x direction, and so on and so forth. Okay, so what will be the partial of f with respect to x? Well, it will be the partial of f with respect to uppercase x and the partial of uppercase x with respect to x. Okay? But in this case, it's easy to notice that this is 1. So this is just the partial of f with respect to uppercase x. Okay, and then, well, the partial of f with respect to x prime is going to be, again, the partial of f with respect to uppercase x times the partial of f with respect to, the partial of uppercase x with respect to x prime. But again, looking by this definition, this is going to be equal to negative 1. So this is minus the partial of f with respect to uppercase x. So we see that we got the same expression but negative. So that means that the partial of f with respect to x is equal to negative the partial of f with respect to x prime. And looking that this corresponds to the gradient of f, this corresponds to the gradient prime of f, where the gradient prime is, well, the derivatives of f, but taken with respect to the prime coordinates. Okay, but we see that they are the same, just the difference is this minus sign. So we can set that the gradient of f is equal to negative the gradient prime of f. Remember, again, these derivatives are going to be taken with respect to the general coordinates, and these derivatives are going to be taken with respect to the prime coordinates. Okay, perfect. So that is enough to show that the gradient prime of 1 over r is going to be equal to, well, negative this gradient over here, but negative this gradient over here is negative this expression over here. So we get minus r over r squared. So that means that the gradient prime of 1 over r is equal to r over r squared. And this is finally the expression that we are going to use. And why is that? Because here on the expression of the electric potential, well, that is what we have. We have r over r squared here. So we are going to change that expression for the gradient that we just found to get the next formula. This formula that I have just written. Okay, so what will we do next? Well, we need to notice that what happens if we take the gradient of P over R. Well, we know that this is equal to, well, 1 over R, the divergence of the polarization, plus it will be the polarization dot the gradient prime of 1 over R. Okay, but look at the expression that we have here. Here is the same that we have here. Okay, so we are going to solve this equation for this term to get that the polarization dot the gradient of 1 over r is equal to, well, it will be the divergence of the polarization over r minus 1 over r, the divergence of P. Perfect. So if we take that and take it into this equation, and remember that we are calculating the potential for a particular vector r, where it points to the coordinates x, y, z. Okay, so this will be equal to the volume integral of, it will be this, the divergence of P over r, minus 1 over r, the divergence of P, all over 4 pi epsilon 0 dV. Okay, perfect. So now we are going to split this into integrals to get that the electric potential is going to be, well, first of all, it will be taking the constants out, 1 over 4 pi epsilon 0, the volume integral of the divergence of P over R, and then plus 1 over 4 pi epsilon 0, the volume integral of 1 over R, the divergence of the polarization times dV, negative. Okay, perfect. And now I want to recall that there is a very famous formula known as the theorem of divergence. Okay, the theorem of divergence that says that, well, if you have a volume integral of, well, the divergence of vector field f integrated on a volume, well, this will be equal to a surface integral of f dot the differential of area. Okay, we are going to use the divergence theorem in this expression here, looking at, well, we have a volume integral, and it's, well, the divergence of a vector field. So we can say that the electric potential is going to be 1 over 4 pi epsilon 0 times the surface integral of, well, the vector field, which in this case will be P over R dot dA, and then plus 1 over 4 pi epsilon 0, the volume integral of, well, let me write this in this way, over r dv. Okay, perfect. And let's first of all look to this term. Well, we have a dot product between the polarization and the A. It's very easy to notice that this can be seen as the polarization dot vector that will be a unit vector normal to the surface, okay, times a differential A, which is now a scalar, okay. So if we rewrite the potential with that taken into account, it will be 1 over 4 pi epsilon 0, the surface integral of p dot n dA over r, plus 1 over 4 pi epsilon 0, the volume integral of minus the divergence of p over r dB. So we need to notice that if we look to this expression, for example, this expression corresponds to the electric potential due to a surface distribution of electric charges. Why is that? Because we know that if we want to calculate the electric potential of that surface distribution of electric charges, we know that we need to take the surface integral of a certain sigma distribution times dA over r. Okay, so this will be like a surface contribution to the electric potential. And in the case of a volume distribution, we know that the electric potential is the volume integral of some distribution of electric charges in the volume times dB over r. Okay, so we see easily that these two integrals have a very similar form to these expressions here. So if we find the bound surface electric charge sigma b, and the b is for bound, as p dot n, and we define rho b as negative the divergence of p. These are going to be the bound density of charges. Okay, so we can rewrite the electric potential phi of r as 1 over 4 pi epsilon 0 times the surface integral of sigma b dA over r, then plus 1 over 4 pi epsilon 0, the volume integral of rho b dV over r. Perfect. So this will be the electric potential on a certain point P located by the vector r. Okay, this will be the electric potential due to a dielectric that is polarized due to, well, any reason. Okay, in general is occasioned by some external electric fields, like in the example that we gave at the beginning of the video. But the case is that the dielectric is polarized, and then we calculate the electric potential due to that material. Okay, so this is the expression that we need to find that electric potential. Okay, and the important concepts here are the bound density of charges, sigma and rho.